Hey guys, my name is Trevor Sullivan and welcome back to my video channel. Thank you so much for joining me for yet another video in the Rust Programming Fundamentals video series on my YouTube channel. Now, the concept that I wanted to cover in this particular video actually builds on top of some of the things we discussed in earlier videos if you're following along with my Rust programming tutorial playlist. So in the last couple of videos, we took a look at the introduction to threading, and then we also understood what scoped threads are, which allow us to share data between the main thread as well as any threads that we instantiate from the main thread. But there's actually other ways of sharing data between different threads within a Rust program. And one of the ways that we can accomplish that is by using a built-in construct in the standard library known as a mutex. Now, if you don't come from a computer science background and the word mutex sounds kind of intimidating, it's actually a very, very simple concept. Basically, a mutex is a mutual exclusion. What it basically means is that you can take a piece of data in memory, you can wrap that into what's known as a mutex, and the mutex helps to guard that data so that only a single thread is able to access that data at any given point in time. That way, if you build a Rust application that maybe has 10 or 20 or 50 different threads running, of course, depending on how many CPU cores you have in your system, then you can make sure that your code can safely access that memory from all 50 different threads, but in a mutually exclusionary manner, right? So we only want one thread to actually have access to that data, but as soon as that thread is done accessing that data, we want to then basically give it back to the system so that another thread can then access that data. So mutexes are actually really simple to understand. We're going to go through and actually take a look at how to code around a mutex and access some state from our main thread from child threads in our Rust application. But first, I wanted to point you to an article here in the Rust programming language book, which is kind of one of the primary sources for learning about Rust in the Rust documentation here. If you go under chapter 16, they have chapter 16 subsection 3 that talks about shared state concurrency. And this example talks a little bit about mutexes. So if you'd rather read about this topic than watch this video about this topic, you can go right here and they do a pretty good job of describing how mutexes work. But in this really simple example that they have right here, basically what we're doing is we create this new mutex, and this just wraps a piece of data, right? In this case, it's just an integer, but you can use other data types in here as well. And then what you want to do with a mutex is call this method called the lock method. And what the lock method is going to do is it's going to give you exclusive control over the data that's been wrapped by the mutex. So inside of this subscope right here within this application, this isn't even a separate thread, right? This is just a subscope within the same main thread in an application. And so what this scope is doing right here is it's calling this lock method that gives this scope exclusive access over this bit of memory that's wrapped by the mutex. And then it unwraps the underlying data type. So very similar to the option type that allows you to get some or none of a value. We basically unbox or unwrap the underlying data, and then we can go ahead and mutate that data as long as we have a mutable reference to the underlying data. Now, in a multi-threaded situation, you have to make sure that your thread is politely giving access back to the mutex, right? So you might think, well, if I'm going to lock this data and have exclusive access to the mutex, how do I exactly unlock it? Well, until future versions of Rust actually have an unlock method on the mutex, currently that's an experimental feature in the nightly builds of Rust, as you'll see in the actual documentation for this module called the sync module, which is part of the standard crate. But in the current version of Rust, basically what you do is you just let that mutex handle go out of scope. It's called a mutex guard, in fact. And once that mutex guard goes out of scope, then the control is handed back to the mutex so that another scope or another thread can then lock and retrieve and mutate the data that's wrapped by the mutex. So it works for subscopes and it also works for thread-based approaches as well. Now, there are other types in the sync module that deal with wrapping different parts of memory, but just to keep things simple so that we really understand what a mutex does by itself, we're just going to focus on the mutex type for this particular video. Now, if you jump into the documentation for the standard crate right here, there is a child module. So let's just go up to standard here. And then if you take a look at the modules, there's all of these built-in modules in the standard crate. And if you scroll down a little bit towards the alphabetical sorted S here, we have the synchronization primitives here in the sync child module. So we go to standard, then sync. And then if we go to the data structures that are exported by the sync module here, you'll see that we have this mutex struct along with the mutex guard, and those two different data structures work hand in hand in order to wrap the data in memory and then temporarily grant access to the memory. Now, if we take a look at the mutex type right here, we can simply create a new instance by calling the new method on the mutex type and then pass in our data. So that'll create a new mutual exclusion lock. And then, of course, there is the lock method right here, which gives us this lock result, which gives us the mutex guard that we can use to have exclusive control over the data that's wrapped by the mutex. Now, if you look for the unlock method right here, you'll see that this is a nightly only experimental API. If you're running one of the production builds of Rust, I think I'm on 1.72 right now, then this unlock function is not going to be available. In general, unless you are doing really cutting edge development, you probably don't want to be using the nightly builds just because there's a lot of unpredictability, things are changing rapidly, and you might just run into new bugs in that nightly build. So for most people out there, you're probably going to want to stick with the production builds, and this unlock method on the mutex itself isn't currently available. So wait a little while for that to come out. It is kind of a nice enhancement to the language, just so that it shows in your code that you're explicitly giving control back to the mutex. But for now, you'll just have to remember that when the mutex guard goes out of scope, the control is automatically handed back to the mutex. All right, so there's another method down here called try-lock. Now, there's a key difference between the lock and the try-lock methods down here. So one is going to give you control back to the thread. The other one is going to block access to the thread. So with the lock method right here, this is the one that you probably just think to use by default because it just has a very clear name. But if you call the lock method, this will actually cause your thread to hang until the mutex is unlocked. What that means is that your thread will not be able to do any other work until the mutex is released, and that thread can then go ahead and grab the lock handle to the mutex. If you want your thread to continue doing useful work while it's checking to see if it can get a lock on the mutex, then the try lock function right here on the mutex is going to allow your thread to continue running if you would like that to happen. So this will go ahead and just not block your code. So you can just periodically check in with the mutex and say, hey, are you ready yet? Are you ready yet? Can I have a lock? Can I have a lock? And if the answer is no, you just go off and do some other work. But maybe every 5 seconds or maybe every 30 seconds, you just go back to that mutex, try to get a lock on it. And if you can't get a lock on it, that's fine. We'll just go do some other meaningful work in the meantime. So those are a couple of patterns that you can use with the mutex type here. So now we're going to jump into some code and actually figure out how this works from a practical standpoint. Before we jump into the code sample, though, I just wanted to remind you that I am an independent content creator. This is my job to help you guys understand Rust and other types of technical topics. So please go out to my channel, youtube.com/Trevor Sullivan. Subscribe to the channel. That really helps me to grow this community and bring you more great content. Also, if you learned anything new by the end of this video, please leave a like on the video and a comment down below to let me know what you thought of this particular video. All right, so let's go ahead and jump into our code here. So we're going to be building on this code that I've previously been creating here. So under main.rs right here, we've got all of these extra modules that we've been calling out to. So what I'm going to do is just comment out any references to the scoped threads module that we previously discussed. And we're going to go ahead and create a new module here to play around with mutexes. So I'll just call this my mutex.rs, and we'll expose a public function from this module here. So let's call this pub fn and test mutex, for example. And then we'll go back here to our main function and we'll say pub mod my mutex so we can use the functions. And then at the end, we'll just say my mutex and call test mutex. So now everything is set up for us to write some code inside of this function that creates a mutex and then attempts to lock access and mutate the data that's wrapped by the mutex. So let's start out by declaring a number, right? So how about let's do score, and we'll say score is equal to an unsigned 16-bit integer. But what we want to do is actually provide a default value. So we'll just do an initial score value of 0. And then we need to wrap the unsigned 16-bit integer in the mutex type. So to do that, we're going to do mutex :new, and then pass in the data that we want to wrap in the mutex. Now, because we haven't referenced the mutex type here in our module, we need to do a use standard sync and then mutex, and that will import the mutex struct so that we can call into that struct and use the new method here in order to instantiate the mutex. So now you can see right here, the Rust compiler is inferring that my score variable is pointing to a mutex that wraps an unsigned 16-bit integer. Of course, if I change the initialized data right here, that'll change the underlying type of the mutex as well. So the Rust compiler is able to determine, just based on the value that I'm passing in, what data type is appropriate for the score variable here. All right, so now we've got this mutex, right? So if we wanted to change something inside of this mutex, let's say we wanted to add 5 to the score. Well, let's say we do score is plus equal to 5, right? Well, first of all, we can't mutate an immutable variable. So you might think, all right, well, let's make the score here mutable, right? Well, we can't directly add an integer value to a mutex, right? So we actually have to get access to the underlying data that the mutex is wrapping so that we can manipulate that value. So you might say, all right, well, let's do score.unwrap or something like that. Well, unwrap isn't even available right there. The only functions that we have available here on the mutex type are, of course, to deal with the mutex itself. So you might say, well, maybe I'll get a mutable reference to it. And of course, we can't do that either. So what we actually need to do is get the mutex guard so that we can access the underlying data. The way that we do this is by doing the mutex.lock, and this lock function right here is going to return the mutex guard inside of a result right here so that we can get access to the data. So let's go ahead and assign the results here to unlocked data, and we'll say let, and then we should be able to get an exclusive lock to mutex here because there's no other code inside of our Rust program here that is trying to lock it. This is the only reference to the mutex and the only call to the lock method. So once we have the unlocked data here, we still need to unwrap the underlying data. So then we can call unwrap right here, and this will be our actual data, right? Because right up here, we get the mutex guard that's wrapping the data, but then when we call unwrap, we actually get access to the data itself. So let's go ahead and try to do data plus equals 5 right here, and you'll see we can't mutate the immutable variable. So let's do mute on data. And I think I also need to call another function here. Actually, no. In this case, what we have is a mutex guard, right? And so in this particular case, I can't just do plus equals 5. What I actually need to do is say data, and then what we can do is use one of these methods right here on the type. So what we can do is say data.add assign, and then we can specify a value that we want to add to the underlying data. And so let's say 5, right? So what add assign does here is it takes the underlying unsigned 16-bit integer, whatever value it currently has, it adds 5 to it, and then it assigns it back to the original mutex. So now what we can do is say, print line, just grab the value here and pass in data. And let's do a debug print value here. And then let's do a cargo run. So sure enough, you can see that we have the value of 5. But what happens if another thread comes along and wants to access this exact same data? Well, in order to unlock the data, what we have to do is make sure that the mutex guard rather goes out of scope. And so what we can do is explicitly do that by dropping the mutex guard. So if we drop unlocked data here, or actually let's try dropping data, then we should have access again to mutate the mutex by getting a new lock on it. So we're going to actually do a multi-threaded scenario so that you can see in practice how this actually works. So let's get rid of this code right here. I'll just comment that out, and then we'll create 2 different threads, okay? So our first thread is going to be a closure. Let's do myfunc. We'll make it a closure here. So if you watched my video on closures, these pipe characters denote the input arguments to the closure or anonymous function. And then we can run some code inside of here, like let's put a semicolon there. So we'll say for I in 1 to 10, we'll go ahead and just add I back to the mutex. So let's start out by getting a lock from the mutex. So we'll do score, and this doesn't actually need to be mutable itself. So we'll say score.lock, and we'll say .unwrap as well. So we'll say let data equal that. And then inside the for loop, we'll just do data.add assign, and we'll pass in whatever I is. And of course, we need to make this data reference mutable so that we can change the underlying data of the unsigned 16-bit integer. And then after the closure ends, so after the scope of the closure ends right here on line 17 with that ending curly brace, then the mutex guard is going to automatically go out of scope and return control back to the caller. So let's go ahead and attempt to call this closure and see if we can access the mutex from the main thread after the child thread actually executes. So what we're going to do is say use standard thread, and you should already know this from our last couple of videos. And we're going to call spawn here so we can spawn a new thread. And now we'll say spawn and pass in our closure, which is myfunc. And then the other thing we want to do is to join, because that will allow our main thread to synchronize with the child thread. All right, so it is saying that the closure may outlive the current function, but it borrows probably the mutex itself, right? So yeah, so it borrows score. So what we should be able to do is move ownership into that child thread. All right, so now what we're doing here is moving ownership of the score into the closure, and that will probably mean that we can't use it after the thread executes, right? Let's go ahead and just discard this result right here. Let's run our application. So it compiles and it executes just fine, right? But we're not attempting to access the mutex after the fact. So let's do a print line here, and we'll say debug output. And then we'll do our mutex dot lock dot unwrap. And sure enough, it says borrow of moved value. And that's because we are moving the mutex into this child closure here. So in this case, what we actually want to do is wrap it in the scope type here. So let's do a scope instead. And we'll say scope. And then we want to spawn a scope. And inside of that scope, we are going to call the myfunc. So we'll do scope spawn, and then we'll do myfunc right here. and put a semicolon at the end. And let's just comment this out for a moment right here to see what we've got here. All right, so we've still got the move keyword in here, but because we are doing a scoped operation here, we don't need to worry about move, and that will allow us to borrow the mutex inside of our child thread here. So now that we've wrapped it in a scoped operation, we are able to borrow the mutex inside of the child thread, but then we still have the ability, because score is still owned by this function, test mutex right here, we can still use that variable from the scope that it was actually declared in. So that's again why you want to generally use scoped threads, because when you start getting into borrowing values from that parent scope, it just makes things a lot easier to deal with. So now if we run this here, we can see we get 45, which is basically 1 through 10 added together. Now let's create another thread, okay? So what we're gonna do is copy this here, and we're gonna create a second thread here. And each of these threads is going to attempt to lock the mutex. And then we're going to add 1 through 10 from each of these threads. So we should have basically double the value of 90 instead of just 45. So now we'll go down here and we'll say s.spawn myfunc2. And then we'll do some debugging statements in here just so that we can kind of see what's going on. So thread 2 is adding I, and that'll just kind of show us the current iteration of this for loop here. And I'm also going to say print line at the very beginning of thread number 2 and say thread 2 is waiting for mutex lock, just to show that it's pausing execution, because lock here is going to block any additional execution of that thread until it does actually receive a lock. And then let's go ahead and copy these into our first thread as well. So we'll say thread 1 is adding whatever I is, and we'll say thread 1 is waiting for a mutex lock. All right, so thread 1 is waiting for the mutex lock. There we go, just had a little visual issue there. So we're spawning both of those threads, then we're accessing the mutex from the main thread after the fact. So we have the main thread accessing the mutex and 2 child threads that are accessing the mutex as well. And if we do cargo run, you can see that thread number 2 is waiting for lock, and apparently thread 2 actually got the lock first. So even though we invoked the second thread after the first thread in our scoped spawn operation right up here on line 33 and 34, thread number 2 actually got access to the lock first. And then thread number 1 is also waiting for the lock. And after thread number 2, the mutex guard goes out of scope, right? So let's go over that really quick. So on line 25, we declare the mutex guard as mutable. And then after the scope ends, after the thread is finished executing, that mutex guard automatically goes out of scope, right? And so then what happens is that thread number 1 is able to retrieve its lock, because it's basically hanging there in the background waiting for the lock, and it goes ahead and does its work. And then the main thread at the very end is able to again get a lock on that same mutex and retrieve the result so that we can display that result. So that's how mutexes work at a basic level. However, there's a little bit of a gotcha. What exactly is going to happen in our program here if one of these threads fails? So what we'll do up here in thread number, let's actually do it in thread number 2, because I think pretty consistently for some reason, thread number 2 is actually causing the lock to be retrieved first. So what we're going to do here is after we get the lock on the mutex, we're going to go ahead and panic and say error in thread 2. So what do you think is going to happen? Well, we kick off these 2 threads. Thread number 2 generally gets access to the mutex first. So what do you think is going to happen when we get a panic? Well, what happens here in this particular case, thread number 2 waits for its mutex lock, it gets the lock, and then it panics. And that causes the entire application to panic, because inside of our scoped threads here, we did not actually handle any panics in the child threads. So normally the scope here just goes ahead and joins each of these threads. So it waits for the threads to finish. But if you don't handle any errors or panics inside of these threads, then the entire main thread is just going to crap out and is just going to crash your entire program. So what we want to do is actually handle things a little bit more gracefully at the thread level, detect if there is a problem, and then see if we can release the lock on the mutex, right? So what we're going to do inside of here is get a couple of handles to each of the threads. So we'll say handle 1 and then dot join, because the join function here is what gives us the handle back. And then we'll say let handle 2 equal spawn dot join. All right, so now we have these two handles. We're spawning the threads, we're joining them. And then what we want to do is to check to see if there was an error. So we'll say if handle2 dot is error, then we want to basically just say something like thread2 had an error. Let's handle it here, right? So we'll go ahead and do a cargo run here. And now we're attempting to handle things a little bit more nicely here. So what you'll see is that it looks like this time thread 1 actually got the mutex lock first. So let's try that again. See if we can get thread 2 to get the mutex lock first. Of course, now it's probably not going to cooperate with me. So what I'm going to do is actually just switch these around. So let's do myfunc2 first, and then we'll do myfunc1. All right, so what you're going to see happen here is that thread number 2 got the mutex lock and then it panicked. But what's happening here is that thread number 1 is never able to get the lock because we never actually dropped the value of the mutex guard, right? So if an error does actually occur in a thread and you don't drop the mutex guard, then the other thread is never going to be able to handle the mutex, right? So what you can do is if an error occurs inside of your program in the thread, we can go ahead and call drop on the mutex guard, and that will force it to be returned. And this is a more graceful way of handling things because now thread number 1 can actually go get the lock, and thread number 2 can just have its error and deal with it in some other way. But at least that way, our thread isn't holding up thread number 1 from executing, right? So that's something that you'll want to be aware of when you are dealing with multiple threads, accessing the same mutex, is being able to handle any errors that occur in those threads and make sure that they politely give access to the mutex back to any other threads that need to access it. Now let's take a look at how the asynchronous method works, where we can try to get a lock, but if we don't get a lock, then we can do some additional work, right? So what we're going to do in one of our functions here is, let's actually drop the panic here. So I don't need to explicitly drop the mutex guard anymore. And what I'm going to do is go in here and we're going to say loop. So once we enter this child thread, we're just going to loop, and then we're going to try to get a lock inside of this loop. So we'll say let data, actually we'll just kind of move this right up here. So we'll move the mutex guard into the loop right here. And we'll also say thread 2 is waiting for the mutex lock right beforehand. And if for some reason we don't get a mutex lock, then we want to sleep for a certain duration and maybe do some other work in the meantime. And then later we'll try again to get another lock, right? Because the try lock method here is going to be asynchronous. So what we want to do is import the sleep. So we'll do use standard time and then sleep. And then we can call the sleep function. Actually, we want, duration here. We're going to use ThreadSleep. So let's import sleep from the thread module. And then we have to pass it a duration, which is why we have to import the duration type. And so we'll say sleep and say duration new. Let's do new. Actually from milliseconds, not new. And we'll just say sleep for 300 milliseconds. All right, so now what we want to do is say after we attempt to get the lock right here, right? So after we attempt to get the lock on the mutex, if it does succeed, then we want to run this code right here that does the add operation for our program. So what we'll do is say if the data is successful in getting a lock, so I think we want a function here saying if it is successful. Let me figure out exactly where that is in here. So actually, I think what we need to do is just try to get the lock, and then we'll actually unwrap it in just a second here. So we'll say let guard equal try lock, and then we'll say let data equal guard dot unwrap and make that mutable. So then on the guard itself, not the underlying data, we want to say, is it okay? And if it's okay, as in it got the lock, then we want to go ahead and run this code here. All right. So it looks like we have borrow of moved value. Let's see what's going on here. And of course, what I just realized I didn't do is actually unwrap the data inside of this if statement here, because as long as the guard successfully got a lock, then I need to actually go inside of this if statement in order to actually unwrap the data. So we're just going to move that statement to unwrap the data right inside of here, and that lets us use the guard variable right here in the conditional statement of the if loop, of the if block. All right, so then we are going to go ahead and sleep after the if block if for some reason it fails to get the lock. And then after the if statement succeeds, then we can break out of the looping construct that we have because our work is finished. So this thread, myfunc2, is going to infinitely loop. It's going to infinitely attempt to get a lock on the mutex for every 300 milliseconds. And if it doesn't get a lock, it's just going to keep looping. And as soon as it does get a lock, it's going to do the processing on the underlying value of the mutex. Then it will break out of the function gracefully, and the thread will finish. And it should drop the guard, the mutex guard, and that'll give control back to the mutex. All right, so let's give this a try and see what we get here. Also, I don't think I really need this error handling stuff right here anymore because we're not going to panic inside of any of our threads here. And so now it looks like thread number 2 was actually first to get the lock. So let me switch these around again. So we'll put the second one second and the first one first. And this time, everything runs normally again. But in order to kind of demonstrate what would happen if thread number 2 was not able to immediately get a lock, it's able to get a lock just because the operation is happening so fast here. But what we're going to do is actually sleep a little bit inside of the thread number 1 here on every iteration of our loop. So let's just say that we're going to sleep for maybe 400 milliseconds for each iteration. So now when we do cargo run, we should see that thread number 2 is waiting for the mutex lock here, and it should be printing that out repeatedly here. So let's see why it isn't doing that. And I'm guessing the reason it's doing that is because we are doing a join operation here. So we're actually waiting for the first thread to finish. So we don't want to join in here. We're just going to do a spawn operation and let it automatically join thanks to the scoped threads. So let's remove the join from there as well. And now we're going to kick off both threads immediately with each other. All right, so this is a little bit more what I was thinking was going to happen here, but I got the threads reversed again. So let's put number 2 first. And this is what I was hoping would actually happen here. So now you see every few hundred milliseconds that thread number 2 is waiting for the mutex lock. And this is that looping construct actually taking effect here, where every 300 milliseconds, it's going to reattempt to get a lock by calling try lock. But then the lock is failing, so we don't have is okay for the guard right here. And so it's just skipping over this entire if block that we have right here. It's going to sleep for 300 milliseconds. And on the next iteration of the loop here, it's going to once again try to get another lock. And so you can see that while thread number 1 is going through every 400 milliseconds and adding a number here, Thread number 2 is continually checking to see if it can get a lock. And finally, after thread number 1 is finished, after adding the number 9 right down here, then thread number 2 successfully retrieves the lock and it does its work, returns back to the main thread, and the main thread is then able to access the mutex on line 51 and unwrap the underlying value and simply print it out. So mutexes are pretty cool. They're very interesting to work with. They're also very easy to work with. So again, even if that term is kind of intimidating to you as somebody who doesn't come from a computer science background, hopefully this gives you a better understanding of how they work and you can implement them into your own programs. Anyway, that's all I had for this particular video. Again, please leave a like on the video if you enjoyed it. Leave a comment down below. Let me know what you thought of this video and subscribe to the channel, and we'll see you in the next video. Take care.